Neuromorphic computing. Let's just stop and think about the human brain for a second. It is an absolute computational marvel. I mean, it can perform what's called exaflop scale calculations. That's a billion times billion calculations every single second. And the truly wild part, it does all of that on about the same amount of power as a dim light bulb. This unbelievable efficiency is kicking off a whole new era in technology. So that leads to a huge question. What if we could build our machines with that same mind-boggling efficiency? And that is the core idea behind one of the most exciting fields in tech today, neuromorphic computing. Yep, that's the number, around 20 watts. Now, to put that into perspective, a supercomputer trying to do what your brain does would need megawatts of energy. We are talking enough to power a small town. The brain does it with less juice than it takes to charge your laptop. So how on earth is that even possible? Well, the secret isn't just in the software, it's baked right into the hardware. The brain's architecture is fundamentally different. It blends memory and processing together. And for the very first time, we're actually learning how to copy that blueprint. Okay, this slide really breaks down the two different ways of thinking. Traditional computers on the left, they work sequentially. It's kind of like having one single super fast chef trying to cook a giant feast, one dish at a time. They're powerful for sure, but they hit this traffic jam called the von Neumann bottleneck, where data is constantly being shuttled back and forth between the processor and memory. Neuromorphic computers, on the other hand, are totally different. They work in parallel, like having a million tiny chefs all working at once. Memory and processing are woven together, just like in our brains. That completely gets rid of the bottleneck and slashes energy use. So, and this is the really crucial point here, this isn't just about writing a new piece of software. Neuromorphic computing is about building entirely new hardware, a completely different kind of chip that's directly inspired by the actual structure of our own neural systems. And look, this isn't just some academic exercise to build faster computers for the sake of it. This tech has some profound, deeply human applications. So let's look at one of the most high-stakes examples you can imagine: brain implants. Modern brain-computer interfaces are incredible, right? They can read neural signals with amazing precision, but that very precision creates a huge challenge: an absolute fire hose of data. For example, a high-density implant like the one Neuralink is developing can generate something like 200 megabits of raw data every single second. That is a massive stream of information coming directly from the brain. But here's the catch: the wireless link, the Bluetooth connection that gets the data out of your body so it can be processed. It can only handle about 1 to 2 megabits per second. It's a classic bottleneck. And the result of this bottleneck is just staggering. It means we are forced to throw away 99.5% of the data before it can even be looked at. We are only using half a percent of the implant's real potential. All that rich, nuanced information from the brain is just gone. So this is the old model. The implant records the data, desperately tries to compress it, and then sends that tiny little fraction to an external computer. It's slow, it creates lag, it loses information, and it's just incredibly inefficient. Now check out the neuromorphic approach. Instead of trying to ship all that data out, the processing happens right there on the implant itself. If you follow the diagram, you can see the chip first records the neural signals. Then it uses something called a spiking neural network, which is a type of AI that actually mimics how real neurons talk to each other to analyze the data on the chip. This lets it learn and adapt over time, creating this smart, closed-loop system that it decides on its own whether it needs to send a signal back to the brain. No bottleneck, no data loss. It's a game changer. Now you might be thinking, this all sounds a little bit like science fiction, right? Something that's maybe years and years away. But the most exciting part of this whole story is that this revolution isn't coming, it's already here. Yet, this brains-inspired technology has made a leap from the research lab straight into the real world, and it's probably a lot closer than you think. So let's meet one of these chips. This is Pulsar from a company called Innatera. It's a neuromorphic chip built for devices that are always on, always sensing the world around them. And because it runs on just microwatts of power and does all its thinking locally on the chip, it doesn't just give you better battery life and privacy, it enables a whole new class of smart devices that don't even need the cloud. This is a really fundamental shift for the whole Internet of Things. So what can you do with a chip like this? Well, in a factory setting, Pulsar can literally listen to the vibrations of a motor. Its built-in spiking neural networks can learn the unique pattern of a healthy machine and then detect the super subtle changes that mean a failure is about to happen. It lets machines diagnose themselves right on the device. Or think about your own home. A small detector with a pulsar chip inside can be hooked up to a tiny radar sensor. It can tell if people are in a room without needing a camera, which means your privacy is completely preserved. It's just a smarter, more context-aware way to keep everyone safe. And this whole shift is really getting the industry's attention. David Harrow from John Peddle Research sums it up perfectly. He says companies are desperate to add intelligence to their products, but without the usual penalties. Neuromorphic chips, well, they offer a realistic way to put that intelligence right at the source on device itself. So we've got this incredibly powerful new technology, and it's starting to show up in real products. But for any field to truly grow up and go mainstream, it needs one more crucial thing, a common yardstick. I mean, think about it. You've got to have standards. You need to be able to compare different chips, to measure progress over time, and to agree on what good even looks like. Without that, it's really hard to build a healthy, competitive ecosystem. And that's exactly where a project called Neurobench comes in. This is a massive collaborative effort with talking nearly 100 authors from over 50 different universities and companies all working together to build a standardized set of tests for the field. This is a huge signal that neuromorphic computing is getting organized for serious large-scale growth. Alright, so we've covered a lot of ground. We've seen the core concept that was inspired by the brain. We've looked at a critical application in medicine, and we've seen the technology arrive in real-world devices and even get its own standards. So what does all this go from here? When you actually lay it out on a timeline, the acceleration is just incredible. The idea was pioneered back in the late 1980s by Carver Mead. Then it spent decades in research labs, but in just the last few years, we have jumped from these academic projects to commercial chips that are in actual devices. The trajectory from here is pretty clear: ubiquity, where this efficient brain-like AI just becomes a seamless part of the world around us. And that leaves us with one final fascinating question. When computers that think more like brains are embedded in all the objects we interact with every single day, from our homes to our cars, even our own bodies, what new possibilities are we going to unlock? What will we create next?